So today we're going to be talking about extreme values of functions. Okay? Basically, we're going to be talking about the maximums and the minimums of a function. Their upper limits. Okay? So absolute extreme values can either be maximum, minimum points on a curve. Okay? They are sometimes called global extremes or absolute extrema. And extrema is the plural of the Latin extremium. So extreme values can be on the interior of, or the endpoints of a function. Okay? So this function right here, the quadratic, okay, does it have an absolute maximum and an absolute minimum? Well, it does have an absolute minimum. This value at the bottom, this is its absolute minimum point. This is the lowest point, the smallest y value on the function. Okay, that is its absolute minimum. Does it have an absolute maximum? It doesn't have an absolute maximum because this function still keeps going to infinity. So the upper maximum, as soon as you say, okay, well, this is the highest it's going to go, or this is the highest it's going to go, infinity, that arrow keeps it going forever and ever and ever. Now notice it is on an open interval, where the left and the right hand side have the open parentheses. Okay? Now this function here, does this have an absolute minimum and an absolute maximum? Yeah. Because these endpoints here are sitting there, this is the lowest or smallest value there it can go. But instead on this side, since my function stops there, that is going to be my absolute maximum. Okay? Really easy stuff so far. Now, this is where it gets a little trickier. Does this function have an absolute maximum and an absolute minimum? Well, it definitely has an absolute maximum. Okay? That endpoint right there definitely tells me it has an absolute maximum. But it doesn't have an absolute minimum. And the reason is because it's that open circle, we're never going to get to 0, right? Now, what's the closest number we could get to without actually being 0? Well, if we do 0.1, what about 0.01? Isn't that smaller than 0.1? And then even smaller than that is 0.001. And then 0.0001. And we could start coming up with a bunch of smaller and smaller and smaller numbers. And there's an infinite number of numbers there. So we never actually get to the smallest number. So we say that it doesn't have an absolutely minimum value because of that open circle. And again, notice that I'm dealing with that open parentheses versus the closed bracket. Okay? And so the same thing here, it has no absolute minimum and no absolute maximum. Okay? So when we put all this together, we look at our extreme value theorem, which is one of those really important ones that we need to remember. If f is continuous over a closed interval, then f has a maximum and a minimum value over that interval. But the main thing that you have to remember is that we're talking about over a closed interval. It has to be a closed interval, which means solid endpoints on both sides. Okay? And it has to be continuous, because if it's not continuous, it might have a break. So for this one, since it starts and stops, has no arrows on the end, this is a closed interval. Now the maximums can be on the endpoints, or they can be in between, on the interior. Okay? Or it could be at the endpoints. Or it could be a combination of both, where this has a maximum on the interior and its minimum is on the endpoint. Okay? But these are all on a closed interval and they are continuous. Local extreme values, okay? A local maximum is a maximum value within some open interval. So we can have maximums and minimums on an open interval, but we call them local maximums or local minimums. Okay. Sometimes we call them relative as well. So this function right here, we have this closed interval. This is my absolute minimum because it is the smallest value this function has. Okay? It's also a local minimum because it can't be a absolute minimum without being a local minimum. This is a local maximum right here. Because if we don't consider any of the other function, this right here would be a maximum value. Okay, so locally in this little area, it is the local maximum. Likewise, this is a local minimum here. Is it as absolute minimum as this one? No, but in this little area, it definitely is a minimum. This one here is our absolute maximum, which is also a local maximum. And then here is a local minimum. So the way it works is that you find all of your local maximums and your local minimums first. And then you decide out of those minimums which one is the absolute minimum. And this one's the absolute minimum. That's why it's got to be first a local minimum before it can be an absolute. It's kind of like sports. You can't be the best in the US if you're not a divisional leader. Right? You can't go to the Super Bowl if you're not a divisional leader first. Okay? Or any other sport. Like if you're talking about high school, you can't be state champs if you're not district champs first. Okay? Same kind of thing. So this has to be at least a minimum in the area before it can be absolute minimum. Okay? So locals are also called relative extremes, relative maximums, relative minimums, and that's the one I use more than anything. Notice that local extremes on the interior of the function occur where the derivative is 0 or the derivative is undefined. So if we look at these here, local minimums and local maximums happen when the slope is 0. Okay? Or at a point where it is undefined. So here, the derivative doesn't exist because it's a corner. So that can also be an extreme value. So local extreme values, a function has a local extreme value at interior points C of its domain, and if the derivative exists at C, then it's telling you that the derivative there has to be equal to 0. So basically this long explanation is basically telling you that anywhere the derivative is 0, you have a local extreme value, a local maximum or a local minimum. Okay? So, a critical point is a place where the derivative equals 0 or the derivative does not exist. That is a critical point of my function. And critical points often become our maximums and minimums. So when we're looking for maximums and minimums, we first find our critical points, where the derivative is 0 or does not exist, and then we test them to find out if they're maximums or minimums afterwards. Okay? So here's the other thing. Not all critical points are extreme values. Okay? Not all of them are maximums or minimums. Okay? But all maximums and minimums are critical points. So maximums and minimums in the interior function always occur at critical points, but not all critical points are maximums and minimums. It's kind of like that square and rectangle thing. Square is a rectangle, but not all rectangles are squares. Same kind of idea. Okay? So these are your steps for finding maximums and minimums. Okay? First step, find the derivative of the function and determine where the derivative is 0 or undefined. These are my critical points. Then, find the value of the function at each critical point. Find the values or slope for points between critical points to determine their critical points are maximums or minimums. And then, for closed intervals, check the endpoints as well. Okay? Because there might be a point on the interior that's a critical point, but then an endpoint might actually be higher or lower, making it the absolute maximum or minimum. Critical points are not always extremes. For instance, the cubic function, the derivative right there is 0. So if we solved this and found the critical points, we'd find a critical point there, but that point right here at 0 is neither a maximum or a minimum, is it? No, this is what we call a saddle point. Because it kind of looks like a saddle, like on a horse. So it's a saddle point. So these are examples of when you have a critical point, but you don't have a maximum or minimum. Also, when we have a vertical tangent, this is undefined here. This is a critical point, but this is not a maximum or a minimum. So we got to be careful. Okay.